Good day, dear students. Today, we are going to speak on the topic of Raman spectroscopy, which is an important concept of spectroscopy. This spectroscopy is useful for your various competitive examinations. So let us begin. Raman spectroscopy is a popular technique for the analysis of molecular structure, and it is considered complementary to infrared spectroscopy. Raman spectroscopy is based on the Raman effect, which was first identified by the Indian physicist Chandrasekhar Venkatraman in the year 1928. The Raman effect is based on scattering of light, which includes both elastic scattering at the same wavelength as the incident light, which we call them as Rayleigh scattering, and inelastic scattering at different wavelengths, which we call as Raman scattering due to the molecular vibrations. Raman scattering is about 1,000,000 times less intense than Rayleigh scattering. Therefore, to obtain the Raman spectra, it is necessary to prevent Rayleigh scattering from overpowering the weaker Raman scattering. Professor C.V. Raman observed that when a substance, whether it is in gaseous, liquid or solid state, if it is irradiated with monochromatic light of a definite frequency nu, the light which is scattered at right angles to the incident frequency, to the incident light, contained lines not only of the incident frequency but also of lower frequency and sometimes of higher frequency. This effect is known as Raman effect. Now the lines with the lower frequency are called as Stokes lines, whereas the lines with the higher frequency are called as anti-Stokes line. And lines with the same frequency as the incident light is called Rayleigh line. So here you can see in the diagrammatic representation on absorption of IR radiation, if the molecule is excited to higher energy level, then whatever the intensity of the incident light is, if the scattered light is of the same intensity, then that is called Rayleigh scattering. Now here you can see the Stokes-Raman scattering, where the light which is scattered is of a lower frequency. This is of a lower frequency, okay, as the initial light. The light which is scattered is of a lower frequency. So here these are called as the Stokes light. Here you can see the light which is of a higher frequency, that is called as the anti-Stokes Raman scattering. Now you can again understand this with the help of this diagrammatic representation. Here you can see the excitation light, or the light which is incident on a diatomic molecule. The light which is incident or the excitation light is denoted by nu0, and the light which is scatters at right angle to the incident light, it is represented by nu. Now here you can see the frequency in case of Rayleigh scattering is same as that of the incident light or the excitation light. So if you get the scattered light as that of the same frequency as that of the excitation light or the incident light, then these type of intense lines are called as Rayleigh scattering. Now here you can see the frequency which is less than the incident frequency. So that is nu0 minus nu. So here we will get Stokes-Raman scattering. And in this case, the frequency is higher as compared to the initial intensity or initial incident light. So here you will get Raman scattering, but these scattering are called as anti-Stokes light. And for understanding the Raman shift, now if nu-I is the frequency of the incident light and nu-S is the frequency of a particular scattered line, and if you take the difference del nu, that is equal to difference of nu-I minus nu-S, this difference is called as the Raman frequency or Raman shift. So thus the Raman frequencies observed for a particular substance are characteristic of that substance. That means whatever Raman shift the value is obtained, that is based on the particular substance, or this shift is characteristic of the particular substance. Now here you can understand properly again the origin of the Rayleigh scattering, then the Stokes line and the anti-Stokes line. Suppose these are the different energy levels shown here. This is the original level and the substance is excited to a higher energy level. Suppose if the scattered light, that is the light, is returned to the same energy level, okay, then this type of scattering is called as Rayleigh scattering. Here you will get the formation of Stokes line where the molecule returns to an energy level higher than the original level. Then here you will get the formation of Stokes line. Here the light returns to a level lower energy level than the original level. Then here you will get the formation of anti-Stokes line. Let us describe the Rayleigh line when the photon strikes the molecule or if the molecule absorbs higher radiation. The energy is absorbed by the molecule and it gets excited to some higher energy level. In case it returns to the original level, here you can see the light is returning to the original level. Since the lifetime of the excited state is very short, so it will emit the same energy as absorbed. And thus we get the scattering which is known as the Rayleigh scattering, and the intense line is known as the Rayleigh line. Now, same description we will describe for the Stokes and the anti-Stokes line. Again you can say with the help of the diagrammatic representation, the formation of Rayling's line where the frequency in case of wave number of the scattered and the incident, this frequency are same in case of Rayleigh line. Here in case of Stokes line, the frequency of the Stokes lines is less as compared to the frequency of incident light. Whereas in anti-Stokes line, the frequency is greater as compared to the frequency of the incident light. Here the frequency is expressed in terms of wave number. That is why we are representing by nu bar S or nu bar I. So the Stokes line, in most of the cases, the excited molecule does not return to the original level. It may return to a level higher than the original level. So this is the suppose the original level, the molecule is returning to an energy level higher than the original level. So thereby it emits less energy than absorbed. This explains the occurrence of Stokes line. That means a part of the energy of the incident photon which is absorbed by the molecule, it remains absorbed by the molecule. So the molecule is having higher energy than before. Now see the example of anti-Stokes line. Here the excited molecule may return to a level lower than the original level. So here more energy is emitted as compared to the absorbed energy. So this explains the occurrence of anti-Stokes lines. In this case, the molecule has less energy than before. Now here again you can see the representation of lines observed in the Raman spectrum which exhibits the following characteristics. Here you can see the intense Rayleigh scattering. These are the Raman scattering Stokes lines and the Raman scattering anti-Stokes lines. The intensity of Stokes lines is always greater than the anti-Stokes lines. Here you can see the intensity of the Stokes line is greater than the anti-Stokes line. The Raman shift del nu bar generally lies within the far and the near higher regions. Raman lines are symmetrically displaced about the Rayleigh line. Okay, so you can see the symmetric displacement of the Raman scattering lines, whether it is Stokes or anti-Stokes lines. Raman lines are due to the change in the polarization of the molecules. So this is an important condition that the Raman lines will be observed if there is a change in the polarization of the molecule. Now, based on this, what are the conditions for the molecules to be Raman active? Or you can see, or we can discuss in the form as which molecules show Raman spectra. When a molecule is placed in external electric field, the electron and nuclei of the molecule are displaced. So thus a dipole moment is induced in the molecule due to the displacement of the electron and the nuclear, and in this case we say that the molecule is said to be polarized. Okay, so when can we say the molecule is polarized? If there is a dipole moment induced in the molecule because of the displacement of the electron and the nuclei, we say that the molecule is polarized. Now suppose E is the strength of electric field and mu is the magnitude of induced dipole moment, then we can write mu is equal to alpha into E, where alpha is the polarizability of the molecule. So you can keep in mind this equation mu is equal to alpha into E, where E is the strength of the electric field, mu is the magnitude of induced dipole moment, and alpha is the polarizability of the molecule. The scattering of light is explained on the basis of polarizability of a molecule. That means for a molecule to be Raman active, vibrations or rotation should be accompanied by change in the polarization of the molecule. In case of infrared spectrum, the production of dipole moment is necessary for vibrational absorption of infrared. The frequencies observed in infrared are not likely to be active in Raman spectra and vice versa. Now, homonuclear diatomic molecules like Cl2, H2, N2, these are Raman active, but these are microwave inactive because there is no permanent dipole moment in case of homonuclear diatomic molecules, and these are also IR inactive because there is no change in the dipole moment during the vibration. So thus Raman spectroscopy is a complementary technique to the microwave and IR spectroscopy. Here you can see the components of Raman spectrometer. With the help of that, you can observe the Raman spectra. Here you have the laser source, then the sample cell where we keep the sample, the wavelength selector, the radiation transducer, and the computer data system where the Raman spectra is recorded. So that was all about the Raman spectroscopy part 1. In the next part of the topic, we are going to discuss about the further part. Thank you.